All right, so we're going to record this. I'm going to go ahead and share my screen. And so we're going to go a little bit more into chapter 7. We basically, last time we discussed what was a hypothesis test and the basic mechanics of it, but we didn't really talk about really do anything with them. So I want to show you today how to go about that. Again, in the class notes section of Canvas, I do have a section, Google Doc for 7.2. We're also going to try to do 7.3 today. I'm going to go into that Google Doc for 7.2. Huh? Did somebody say something?
Oh, I think that was just my background thing that I
Okay.
shut off.
Okay. All right. So here we are in 7.2. We talked about the mechanics of basically what a hypothesis test is last time. And today we're going to actually do an example of one for a proportion. So if we're trying to say something about a proportion, we're going to look at that example. Then we're hoping to get into one that talks about with a mean. And I want to make the comment that that I'm not showing you how to actually physically go and calculate the formulas for these, because that's not the important part of a hypothesis test. The important part of a hypothesis test is actually being able to make a guess, collect the data, go do the hypothesis test, and then come up with a conclusion based on that. The calculation part of it is actually not something you want to do by hand in most cases. Today's you could do it by hand because it's not that much, not very difficult to do by hand, but it really isn't about doing that. In some cases, it's almost impossible because you've got thousands of data points and you wouldn't want to be using this stuff by hand. So we are going to be showing you how to do this all in R. There are many different parameters we can test. We're going to be looking at a population proportion. So this is where you're saying, you know, what % of people think a certain way, or 1% of people like a certain thing, or what % of people are dying of the coronavirus in different countries. Those are different questions you can actually ask yourselves. I just got something on my news report that said that the proportion of people who died in China was higher than what the Chinese are saying. Whether that's true or not, we don't know, but we could test it and we could go collect some data on it and see what happens. So these are all things that we could actually look at doing, and different questions we want to do. If we're going to test a proportion parameter, the first couple of things I want to mention is P is usually the symbol we use for proportion. This is a population proportion. We use P for that. Usually we use Greek letters for the proportion for population values. But the Greek letter for P, does anybody know what the Greek letter for P might be?
No.
What's a Greek letter that starts with the letter P?
I don't.
Phi?
I, there's psi, and there's phi.
How about pi?
Oh,
It'd
yeah.
say pi.
So the Greek letter P, equivalent to P, is pi. And if I write down pi, what would you think?
3.14.
3.14159, yada, yada, yada. So you would think it's something totally different than an unknown value. So we try to stay away from the Greek letters here. We do want to talk about the sample symbol. It is a p hat. We put a little hat on it if we're using sample values and we don't have a Greek letter for it. But, you know, again, don't get hung up on the symbols. The symbols are not the important thing. We've been doing a little bit of proportions already. We did these in probability. You look at how many times did you get what you wanted over how many times did you do the trials. So that's all it was when we did proportions back in probability. That's all it is now. You can look at how many times did you get that thing, which we call a success, over how many times did you repeat the experiment. So we can calculate that. All hypothesis tests are done the exact same 6 steps, which we haven't actually gone through yet, but we're going to kind of show you what those steps are. The very first step of every hypothesis test would be to actually state what your variables are and what your proportion, your parameter is. So in this case, we'd state our random variable and our population proportion. So X would be the number of successes, whatever you consider a success, and P, your proportion, is just the proportion of successes. And then we write our hypothesis Remember, there's an HO, which is your null, an HA, which is really your alternate hypothesis, but it's really what you want to do. It's the question you're asking. And we're going to go through an example of doing these, so I don't want to spend a lot of time talking about each one of these. I just want you to see that I've written out all the steps here in this Google Doc for you to look at. But we're going to actually go through and talk about and do an example to show you how they work. Every test, before we do that, every test has what we call assumptions. These are things that must be true. Some people like to call them requirements. Some people like to call them, actually, I guess I've only seen assumptions and requirements. And so it's a good way to think of it, as these are things that must be true in order for the test to be valid. In other words, in order for what we're gonna do and say is actually something we can do and say. In almost every assumption of every hypothesis test we're gonna do is to look at what kind of sample we take. So what kind of sample are we normally taking in this class?
Random sample.
Random sample. So our first assumption you're always going to see is that you took a random sample. So the sample is a simple random sample. You would just state that in words, and then you kind of describe how did you take your sample? How did you make sure your sample was random? What did you do? Sometimes, especially if you're doing problems that are already written for you, it's written there that it was a random sample. But sometimes you actually have to go physically collect the data. The second assumption of a binomial, now these assumptions are only good if you're testing a proportion test. If you're testing any other parameter, these are not the assumptions you use. So these assumptions are only if we're testing a proportion. So the other thing is that you always have to have the binomial, conditions for binomial distribution are satisfied. So that's what you would state. So remember, there are three things, because you have a test due tonight on this. There are four things that must happen in order for, so I don't know why I say three, there's four conditions that must happen in order to be a binomial. One is that you have to have a fixed number of trials. What's the second one?
2 responses.
2 responses. Okay, so you have to have only 2 responses. There's a third one.
Oh, hold on.
How are the trials related?
One doesn't affect the other.
Yeah, so the trials are independent. And there's a fourth one. Anybody know it? The fourth one was actually one that a lot of you left off when I graded the homework on this. And that is that your probabilities doesn't change from trial to trial. So you want to make sure you look at all 4 of those and make sure that all 4 are true. And then the last assumption in a binomial test, a proportion test, is that your sampling distribution of your p hat is well approximated by a normal curve. And remember, we would normally tell that that was happening by looking at our normal density plot and our normal quantile plot. This doesn't have that. This is where we're collecting qualitative variables. So you're not going to be able to plot anything up. In this case, we just kind of looked at, did we have a big enough sample? So all of them are done this way, where you look at your N, which is how many trials you took, times your probability, whatever that probability is. You see if it's greater than 5. Do the same thing with N times Q, where Q is just 1 minus P. And that just makes sure you have a big enough sample. So if all 3 of these assumptions are met, then this test is valid. If they're not, then the test is not valid and you shouldn't be doing this test. All right. So we're going to do some things about this and show you how this works. Your next step would always be your calculations. We'll show you how to do that in R. Then you're going to have your conclusion, and your conclusion for every hypothesis test is to say whether or not you can reject HO or fail to reject HO. So if your p-value, which you're going to get from your calculations, is less than whatever alpha level you picked, then you're going to reject HO. If it's not, then you're going to fail to reject HO. And then your interpretation is you either have enough evidence to support what you were trying to show, Well, you don't have enough evidence to support what you were trying to show. So like I said, we're going to go through some examples of how to do this. So here's my example. And this one is not using a data set. There are ones that can use data sets. This one's just not. Most of the rest of the ones we're going to do and hypothesis of means will all involve data sets. This one's just going to require just knowing some data we collected. So in 2016, there was a presidential election. I think you all know that. 55.7% of voters voted in that election. So a recent study by Hill Harris X poll was conducted online among 1,000 voters, and they found that 615 said they would definitely vote in the 2020 election. Now, the 2020 election is this November, so we have some time before this happens. What we want to know is, does this show that there's a larger proportion of voters voting in the 2020 election, presidential election than in the 2016 presidential election?
Well, he could be lying.
They could be. You know what? You have no idea. You never know if people are lying to you, ever. So you have no idea. This is the data we have, and we have to go with this data of what was said. We have no idea. And remember, a different sample will give you totally different answers. So this is just on one sample. You have no idea if your answer is going to be right. You don't know if they lied to you or not. But this is all we've got. So unfortunately, that's what we have to go with. Is we have to hope that they weren't, and we're going to test to see based on this data we have, see what we come up with. Now, why can I never remember this guy's name? Silver is his last name. I can't remember his first name, but he runs the 529 site, and they have actually do polling, and they actually collect data. They actually take different polls and put them all together. So they actually would not just use one poll, but they use a whole bunch, and they get a little bit more accurate answers because of that. But we still don't know if these things are happening. There was actually a Calvin Hobbes cartoon years ago where he just made penny answers. And he says, I just love messing with data. And it's true. People can do this all the time. People lie all the time. Even when you ask somebody something as mundane as what's your favorite color, you don't know if they're lying or telling you the truth. Unfortunately, that's always going to be your case. So we're going to base this off of the fact that we're going to have to trust that these people didn't lie to me. And that's the best I can do. All right. So first thing I want to know is, what did I measure off of people? So remember, your measurement is your variable. And what was I measuring?
Percentage of voters that voted in the election?
But I measured, sorry.
Wouldn't it be whether or not they vote in the 2020 election?
Yeah, it's their response. It's not just a voter, because a voter, I can measure anything off them. I can measure their IQ, their salary, their race, their ethnicity. There's lots of things I can measure off of them. My question is, what did I actually measure? And I guarantee you, an opinion is not what you think of as measure, but it is something I can measure. So it is actually the response to if they're going to vote.
Okay, so you don't just say if they're going to vote in the 2020 election, say their response?
Yes.
Okay.
So the variable is the response to if they're going to vote or not in the 2020 election. So that is actually my variable, but we're going to talk about something called a random variable. When we're dealing, whoops, I just can't spell random. When we're dealing with quantitative variables like this is, I'm sorry, qualitative variables like this one is, this is qualitative or categorical variable. We actually want to count something from this information. So my random variable is what I'm going to count. And what am I going to count from all these responses?
Yeses or no?
It's not ordinal, because it's not, there's no one where it's better than the other.
Here's
It's
yes.
just whether I'm going to vote or not.
Whether they say they will vote.
Right, whether they say they're going to vote. Their response. So what am I looking for, though, on this? What am I trying to say?
That there's going to be more people voting in 2020?
All right, so what am I going to count if I want to say there's more people voting?
The number of people that said yes.
Okay, so the number of people, of actually voters.
Oh, then, yeah.
is
So
missed
like
out.
for these kinds of questions, when it says to just state the random variable, do you also want us to state the regular variable as well?
No, you don't have to. I just thought I would just to help you see what's going on. But
Yeah,
you don't have to. You can just do the one of and not the other.
as
I
long as
do
we.
need the random variable, but you can do the other one if you want to.
Okay.
Just can't type. All right. Now my parameter in this case is proportion, and I know that because of two things. Is I'm dealing with counting something, and I also see this very important word right here, proportion. So you want to look for words like that. Those words will be in your problems a lot of times. They will tell you, hey, we're dealing with proportion. That's my parameter. So look for those kind of words. Critically read these things. Don't just read it and say, I've read it. Read it and think about what it is. So what is my proportion in this tank? I'm going to actually write parameter. Parameter is the proportion. Proportion of what?
Of people that will vote versus people that will not vote.
Well, it's just, I can only do one thing. So it's proportion of people who will vote, right?
Yeah.
So proportion of voters who will vote in the 2020 election. All right, so I'll fix that typing. The other thing to notice is that my random variable was a number of voters, and notice all I did was take off number and replace it with proportion of voters. So these are exactly the same, except that word number changed to proportion. All right, so now we're going to write our hypotheses. And I usually start, even though HO is usually the one we write first, I'm going to start with HA. Because HA is what I really care about. So what am I saying about this proportion of voters who vote in the 2020 election?
It'll be higher than the proportion of voters that voted in 2016 election.
Okay, so I can actually write that. The proportion of voters who will vote in the 2020 election is more than, do I know how many voted in the 2016 election?
No. I mean, we can find out, but no,
Do I not know?
it does not say.
It says a percentage.
Yeah, it
Just
says it right here.
7%.
So very first sentence actually says what that percent was in 2016. So instead of using the words 2016, let's actually stick that number in there. So I'm actually going to say is more than 55.7%.
Okay, and the numbers that we do have is that we have the out of 1,615 say they will vote.
So what does that 1,000 represent? Is this a population or a sample?
That's your sample.
That's my sample, yeah, because there's only 1,000 people, and there's way more than 1,000 people in the United States. So this 55.7 is from the 2016 election. This other information is my data I'm going to use. Okay. I can write this. Go ahead.
No, I was just confirming I understand.
Okay. I can write this in a symbol if you want. So instead of writing all these words out, I can say, if I give the proportion a name, so if I actually say proportion is usually written as a P, if I say P equals, then I can say, what about P? I can say P more than would be what symbol?
You mean
Mathematical
what would
symbol.
The greater than symbol be?
Yeah, the greater than symbol, 0.557.
Okay.
So I can write it instead of words, I can write it mathematically out in symbols. Again, that's really up to you as to which one you'd rather do. I will usually write things in symbols because I'm too lazy to write out all the words.
That's fair.
Okay. And then my HO is always going to be that they're just equal. So I'm going to say it's a proportion of voters who will vote in the 2020 election is the same as 55.7%. Again, if I want to write that in symbols, that would be HO. P equals 0.557.
And we're just ignoring the P, like the chance of being P being less than 0.557. We're just ignoring that.
Yes, we're just ignoring that. We're
Okay.
not really worrying too much about that right now. You can actually, if you wanted to, you could write less than or equal to here. And a lot of people do. I prefer not to, but a lot of people actually will write less than or equal to.
Okay.
All
So in
right,
other
so
words,
there's,
HO is just everything but HA.
what was that?
So HO could sometimes be called like everything but HA in this case.
Everything but HA, yes. Okay. The only other thing we also sometimes do here is we write down what our alpha level is. Alpha level is also known as your level of significance.
So is that 5% level is?
That's, well, did we want 5% in this case, or what level did I want you to test it at?
It says test this at 5%.
Okay, so that is 5%, so that's my alpha level. So my alpha level in this case is the 5%. Again, if you want to, you can put in the symbol. Again, if you want to use symbols, you would go under Insert and Equation, and then we're going to do a new equation, and we go find the Greek letters and find alpha. So you could write that in. And 5%, by the way, I'm noticing a few of you are having a little problem with remembering how to write your percentages. 5% means you move the decimal point 2 places to the left. That gets you 0.05. So I'm seeing some of you say, well, 5% is 0.5, and that's 50%. So just make sure you pay attention to how to change percents to decimals. Okay. All right, so there's that. Now, our next step, and this is the part that people have trouble with because they forget this part, the state part. This step is actually to first state the assumptions. This is to make sure you understand what was supposed to be true, so that you can make sure when you go to do the collections, you actually make sure it actually is true. So you want to first state what it is, and then you want to check to make sure it's right. So I'm going to state, the very first assumption is that we had a random sample of, now what did I measure? And this is where it's actually good to write down your variable. What was my variable?
Response to if they're gonna vote.
And how many did I collect?
1,000.
Yeah. So I collected 1,000 of them because it was 1,000 voters I asked. So I had a random sample of 1,000 responses to whether or not they're going to vote or not was taken. You do want a sentence here, so you do need to actually put a verb in here. I may be a math teacher, but I do know that sentences have subjects and verbs. So you do need a verb here. So I've just put that in. Thank you. Somebody fixed my stuff. Thank you. Now comes the check. So now we're going to check it. And so I usually write state. This is what I stated. And then I'm going to go check it. So I'm going to go up here and see, did they tell me what kind of sample they took?
No.
There's
No,
a
they don't
poll,
actually
so
tell.
that would be a random sample.
Well, it's supposed to be a random sample, but they don't actually say it. They said they conducted it online. Online does not mean always a bad sample. There are certain samples that can be done online that are done just, they email you the information, you send them back. So that's not a problem.
That
I've
could be
never
a
heard of
bad
this. Go ahead.
sample, though. That could be a bad sample because they could pick and choose who's getting it sent to.
But
use
see, I
some
don't
things.
know, but I also would hope that this Hill Harris X company does a good job, but I also have never heard of them. So if this had said Gallup, I'd probably be okay. This has said 529 group, I'd probably be okay, but I've never heard of the Hill Harris X group. So I don't know what kind of sample they took. So I have no idea if this is a random sample. So my check, all I can say is it is unknown.
Do you want us to just assume it's unknown if it's not stated for these problems?
Yes.
Okay.
So it's unknown what kind of sample was taken. So this assumption may not be met. Now, I should mention that I said that if the assumptions aren't met, you can't do the test. But for classroom purposes, do the test no matter what. So if all your assumptions aren't met, still do the test, because we're trying to learn how to do all the steps. So don't worry in the homework if they don't all meet. Just go ahead and do the whole thing. But do realize that you go to do a hypothesis test on your own, you want to make sure this happens.
Do you want
If
us
you're
to
doing a
state-
hypothesis test yourself, you should make sure it's a random sample. That shouldn't be a hard thing for you. Go ahead, Jacob.
do you want us to state, like in the homework, that if they're not met, even if we still do the calculations, do you want us to say in our answer, but the assumptions were not met?
That's a perfectly valid thing to do.
Okay.
All right, now the second assumption, notice, by the way, I wrote this in terms of the problem. I didn't just say a random sample. I said a random sample of how many and of what. So make sure you actually state that. Don't just say a random sample was taken. That's the general thing up here. But I want to see actually in words for you to actually say exactly what it is. So trying to write it in general in terms of the problem is a good idea. Now the second assumption, and on this one, the second and third assumption is not a big deal because they're a little weird. But the second assumption is that the conditions of the binomial distribution are satisfied. So you can actually just write that. You don't need to actually type something in terms of this problem. If you want to, you can, but you don't really have to. So I'm going to back down here to my assumptions, and I would just say my stating is that the conditions of the binomial distribution are satisfied. My check is now to go through all four of those things. So
There is an even number of choices in this matter. It's yes or no.
okay, so there are only two choices, two outcomes. Yeah, yes voting or no. Now, technically, there is the I don't know if I'm voting yet. We're gonna go with just people giving two answers at the moment. All right, what's another thing that has to be true?
One can affect the probability of another.
All right, so you not voting, is that gonna affect my not voting?
No.
Hmm.
No. So the fact that one person votes should not affect the next person voting, the probability of the next person voting. And this is true unless it wasn't a random sample. If it's not a random sample, if they asked all of my friends and we just asked all my friends, we're all going to vote. So that's not a very accurate thing to do. So hopefully it was a random sample, not just asking your friends and so forth. Okay. All right. Then what's another one?
Fixed number of trials.
All right. All right. And are there?
Yeah, there's only 1,000.
Okay. So there were only 1,000 people asked. So
Did
there
it
were
say
fixed number
asked,
trials.
or did it say that only had responded? Okay, it was conducted online among 1,000. So yeah, they're
Yeah.
asked.
So a lot of times what pollers will do is that they want 1,000 and they will keep calling till they get 1,000.
Got it.
Okay. And then the last thing is what? There's one more, the one that everybody forgets.
The probability doesn't change with the amount of trials.
Okay. The probability of a person voting is constant from trial to trial.
I think the reason why people forget that is it's like the exact same as the second one we said, how one outcome does not affect the other. I think
So
that's why it
that
gets.
could be the truth, but it kind of isn't. So if you think about it, if I were to take a multiple choice test, my first question only has 4 responses, but my second question is 5, then my probability changes from each question.
But the answer to number 1 does not change the answer for number 2.
Right.
Got it.
Okay. All right. All right, so there's that state and check. And now the third one, again, is in this case, is just one that we can just state directly as it says. The third assumption here is that the sampling distribution of p hat, which is the sample proportion, is well approximated by a normal curve. So I actually would just state this one exactly as it is, and then I'll show you how we check it. So
we're
the
allowed
p hat,
to paste it?
go ahead.
So if it comes on a test, we're allowed to just copy paste that.
You can just copy paste it. Yeah.
Awesome.
Okay. Just like I just did. I love to copy paste. I'm too lazy to not. So remember that p hat is your sample proportion. All right, so it's what we get from our sample. All right. And the way we check this one is we actually look at your sample size times what HO says P is. And this is the purpose for HO. HO tells you what P is equal to. So in this case, my N was 1,000. What does HO tell me that P is equal to?
0.557.
Yeah, and that's really where HO comes in its role, is it tells you what that value is. And if I multiply this together, that's 1, 2, 3, that's 557. Is that bigger than 5?
Yes.
Oh,
And then
because
you
I was
also-
saying that the sample size is large enough. That's what it's going for.
That's what it's going for, is did you take a big enough sample? Then you're going to do N times Q, and Q is equal to 1 minus P. So Q would be 1,000 times 1 minus 0.577. So I don't know what 1 minus 0.577 is.
That would be
0.44.
What is it?
0.443.
All right, so and you multiply that by 1,000, you get 443. Is that bigger than 5?
no,
443 is not bigger than 5?
no, it is.
Is
Okay. All right, so since both those things are true, that means, so the sample proportion can be approximated by a normal curve. Yeah, fix my spelling all the time. Thank you so much. You can't fix it on the board, but you can fix it here. All right, that makes sense? So
yeah.
that means this assumption's been met. This assumption's been met. The only one that's not so sure about is that first one of what kind of sample was taken. I should probably research who that group is. Like I said, if it was Gallup poll, there's a bunch of other polls that are pretty good out there that we can usually trust that they did a random sample. NAU has a social conditioning group that does a bunch of stuff. So there's a lot of ones you can trust, but the other ones, if you've never heard of them, you kind of have to think about it. So now we're going to go and do the calculations. I'm going to actually show you how to do this in R. So I'm going to bring up RStudio. You're where I am, right? You're seeing me go to RStudio? Okay, I want to make sure I picked the right thing when I shared my screen. You can open up, there is an RMD file for chapter 7 homework. You can open that one up and do everything in there, or you can just do it straight in the console part of R. We're just gonna do it in the console part because I don't really need anything else. This is a proportion test. So the R thing is prop.test. And it actually will come up, so prop.test comes up. And then it kind of tells you right here what you're gonna type in. You're gonna type in your X value, your N value, and you're gonna say P equals whatever your null hypothesis says. And then we're gonna do alternative equals, and you can then say greater than or less than. All right, so that's what we're gonna type in. What was my X value? What was the number of people who said yes from my
615.
what is it?
615.
Okay, 615. So we'll go back to R. And we type in 615 here. Then what was my N?
That's 1,000, isn't it?
1,000. Then P equals, this is what HO says P is equal to. What did HO say P was equal to?
0.557.
And again, this is also the purpose of HO is to say what number you put here. Okay. And then alternative, this is where you say what your alternative hypothesis said. So sometimes if you're doing a not equal to, you just leave this off. But sometimes it actually is a greater than or less than. In this case, was this greater than or less than?
Greater than.
Greater. So you're gonna put in quotes the word greater.
Oh, okay.
And then that's it. And you hit enter. And I'm now gonna go copy this and put this in my calculation step right here so we can go look at all of this. Okay. So we're here in the calculation step. And here's what I typed in. So this is what I typed in. And notice I can just highlight all of that stuff from RStudio. I just highlighted all of it, copied it, and I pasted it directly into where I am in my document. And you can do that all the time. Okay. And what I actually see is, this is what I typed in. So it just reminds me. This very first thing here says a 1 sample proportion test with continuity correction. This is actually something that R does. A lot of people do this continuity correction. So I just leave that there. But the most important thing is telling me I did a 1 sample proportion test. If you didn't, if that's not the test you meant to do, it'll say something different. So make sure it actually says the kind of test you want to do. This is called a 1 sample because there's only 1 sample taken, those 1,000 people's responses. Okay. Then it tells me what data I typed in. So this is a good way for you to check to say, did I actually type in the right numbers here? It was supposed to be 615. Make sure that's what it was in the problem, that was your number of people who said yes. Out of 1,000, that should be your N, so make sure that number was correct. It's telling you what your null hypothesis was. So this is basically telling you, I did want to put in 0.055, 0.557 in for my null probability. And then it starts doing all these calculations. This here is what is called your test statistic. When we were back doing, talking about z-scores, we were talking about if a z is more than 2 or less than -2, we considered it unusual. Or rare actually was, well, rare was minus, so it's uncommon. Rare was -3 and 3. So this is kind of that same idea as to how far away it is. This is a different calculation from a z, so you can't compare it with 2. But it is kind of on that same place where you can actually compare this with something. We're going to care more about this p-value over here. This thing that says p-value, that is your probability that you actually found that value, given that your HO was true. So given that you got this value, could your null hypothesis still be true? So how unlikely is it that your null hypothesis is true, given your data? That's really what this represents. So your p-value represents how unlikely is it that you found this data given the null hypothesis was true.
In this
So in
case,
this,
it's
go ahead.
0.01. I said, and in this case, it's 0.01% basically.
Yes. So 0.000129 is about 0.01%. That's pretty dang small, isn't it?
And that's for our null hypothesis being true?
That's for, not for the null hypothesis being true, that you assume the null hypothesis was true. This is how likely it was you could find this data that you came up with, given that the null hypothesis is true.
Gotcha.
So is it likely that you could find this data given the null hypothesis is true?
No.
No. All right, we're going to talk a little bit more about that in a second, but I want to mention there's a couple other things it tells you. It tells you your alternative hypothesis is greater than. That gives you that information also. It also tells you your sample estimate of p. So in other words, if I took the 615 and divided by 1,000, I would get 0.615. Which of course you can do that calculation without R, but if these are nastier numbers, it's nice for it to give you. So now we're at our conclusion statement. So you just told me it was very unlikely that you would actually get this data given that HO is true. Right? You just said this data the likelihood of finding this data given that HO is true is only 0.01%. So that means, can you really believe that HO is true? That's the only thing you can control, is that you were given that information. Can you really believe that anymore? Can you believe HO is true?
No.
No.
No. So we're going to reject it. So we reject HO since the p-value is less than my alpha. Okay. And that's it. That's
So-
all you say with the conclusion.
Uh,
Now, the interpretation is the important part. This is the part where you actually say, hey, I have evidence to prove what I was trying to show, or I don't. And so if I'm rejecting my null hypothesis, which is way back up here, if I'm saying this is wrong, that means I now have evidence to support this one. So if I can say reject HO, the only thing left for me to say is HA must have some evidence. So that's my interpretation. My interpretation is there is evidence that the proportion of voters voting in the 2020 election is more than 55.7%. And I'm good. I have evidence for that. Is it right? I don't know. But I think it is. I think I did okay. I'm hoping people didn't lie to me. I'm hoping everything worked out. But that's what I got. Everybody cool?
Yep.
Yeah.
And that's it. That's all there is to these hypothesis tests, is doing this kind of information. And you're just trying to follow kind of along with this. But again, this calculation step isn't the important part. We have computers that will do that part for us. It's making sure you understand all the rest of it and can put all this together to do your conclusion and do your interpretation. That's the important part. And every hypothesis test we're going to do from here through the rest of the semester will follow these same 6 steps. And you just need to make sure you understand kind of what is the basis behind these and what's happening. Okay?
What would we do if our confidence interval or if our alpha was not 5%?
And if your alpha is not 5%, you still compare to it. So if my alpha level is 1%, I still would compare my p-value I calculated to that 1%.
Oh, I see. So that has nothing to do. Okay, so we don't change anything for the actual part in R. Nothing's.
Nothing changes for R. That we will be talking about this idea of this confidence interval, hopefully next time actually. And we'll talk more about what this is. And this is actually where more people are doing these days, and the ASA actually suggests you do confidence intervals more. We're going to talk more about this and how you can control that, but don't worry about it right now. So your alpha is just what you set and compare your p-value to.
Got it.
Okay. All right. I'm going to stop sharing for a moment, and I'm going to stop our recording and start up for the next section. Okay.